All right, welcome to the last example, example 2 in 7.2 for Math 30-1. And it's everybody's favorite one, which is modeling a graph using a function. That's tricky. It takes a lot of practice. Right off the bat, we're going to try to read into the question. And I think that the hardest thing for students is the growth rate. And in order to find C, it's the concept that we have 100%, right? The coffee is, 100 degrees Celsius initially. And then it's saying that we're losing 25% every 5 minutes. So if I'm losing 25%, it's really important to recognize that what that means is that we have 75% of what we had. Now, in general, we don't really use percents very often in math. We use their decimal versions, and 75% is 0.75. Now, if you think about what that's saying, is that every time the time goes 5 minutes, we lose 25%, so we have 75% of what we had remaining. Now, this is why exponential functions are asymptotic. If I take away 25% of what I have again and again and again and again, I never actually get to zero. I keep getting smaller and smaller and smaller and smaller. And certainly, kind of realistically in reality, it'll get so close that it'll be zero, right? If I try to cut, a quarter off of a piece of metal forever, eventually that metal is going to be so small that I really can't cut anything. But mathematically, it's very important that if C is equal to 70 or 0.75, we're never actually going to have this, cup of coffee be zero. Or even, specific to this question, if I put that cup of coffee in a room that's 20 degrees Celsius, it's not actually ever going to reach 20 degrees Celsius. Now, we know that that's not really all that realistic because eventually it'll be so close that we can say the cup of coffee is 20 degrees Celsius. So don't get too caught up in the horizontal asymptote concept. It is much more important the idea that we start with 100% and then we gain or lose whatever whatever the question tells us, basically. All right, now it's also pretty important that the cup of coffee is immediately starting to cool, so H is equal to 0. Where you may have an H value is if, I heated up my cup of coffee and then I started the timer before I took it out of the microwave. So maybe for the first 5 minutes, because I'm, I don't know, changing the diapers on my kids, whatever it is, I left the coffee in the microwave. So it didn't cool for the first, 8 minutes. That's not the case here. It was immediately brought out into, the environment. The other one that we're going to do, though, is that it is saying that it is decreasing every 5 minutes, which means that my B parameter is 1/5. And that's really just there to make sure that as X increases by 5, we end up multiplying, or I suppose putting that exponent onto our base, the growth rate. In this case, decay rate, sorry, not growth rate. Now, where that 1/5 comes from is the idea that if it's happening every 5 minutes, then as X goes up by 5, it should increase the exponent by 1. Now, what that looks like, I'm going to start writing this equation out. We still don't know A yet, but now that we have 0.75 to the power of 1/5 times X, and then we'll deal with the K in a second here as well. We need to make sure that every time X goes up by 5, we multiply by 0.75 another time. So if I made X equal to 5 in this equation, I would multiply by 0.75 once. If I made X equal to 10, it'd be multiplied by 0.75 squared. At 15, it'd be 0.75 cubed, and so on. That's kind of the, if you look back to that general exponential form, which is y equals a times, it's not b, sorry, c to the power of t over p, we've basically identified the p, which is the length of time for the growth or decay rate to happen. All right, the next, and I think it's probably the easiest of them, is the k value. Because remember, I talked about how the horizontal asymptote is always at y equals k. Well, this has a horizontal asymptote at y equals 20 because the graph has been shifted 20 units up. So we know that k is equal to 20. I'm going to write this as x over 5 now, plus 20. Now, a lot of students, because of the general form that I kind of butchered over here, think that A is the initial amount. And if there is no vertical translation, then yeah, you're right. A is the initial temperature, amount of money or whatever that is. But because of that vertical translation, we can't say that. So what we're going to do instead is look back up on the graph and grab a point off of it. The easiest point is the y-intercept, which is at 0, 100. And we take that coffee out of the microwave or whatever it is 100 degrees Celsius, and then it starts to cool down because of the room. If we know that point, keep in mind that points are x, y, I can put in 100 is equal to a times 0.75 to the power of 0 over 5 plus 20, which means that 100 is equal to a times 1. Anything to the power of 0 is 1 plus 20. I'm going to subtract 20 from both sides, and I get that 80 is equal to A. Now, what that allows me to do is come up with an exponential function that models the temperature of this coffee, which is going to be y equals 80 times 0.75 to the power of x over 5 plus 20. Now, I'm a big fan of checking to make sure that it worked. And the way that we would do that is I use Desmos just really quickly to make the window settings the same. You could put that into your calculator and then make sure that you have the same scale. So I set this up to be the exact same scale, and this would allow me to predict that temperature of the coffee as time kept on going. Now look at, this is 100 minutes. That's a long time for a cup of coffee to sit at room temperature. The temperature's still not actually 20. It's 20.255. Now if I carried this graph to the right, how many minutes are there in a day? 60 times 24, so right around 1500. Look at what the temperature is at, Desmos gave up. It just gave me 20. That number is still not actually 20. If we looked at maybe a higher accuracy tool, maybe I'll go back a little bit. Sorry about all the kind of jagged motion here. That if I look at, still too close, maybe 200 minutes. Yeah, you can see how Desmos starts to give up after the 1000th. So after 205 minutes, the temperature's still not 20. That is that asymptotic behavior that is very, very important to understand when we're dealing with these types of situations. Okay, I answered the second part. Oops, sorry about that. I got to find the file again here. Determine how each of these parameters are related. The big ones is that the 20 is where the horizontal asymptote occurs. The over 5 is the growth / decay period, or how long it takes for that to occur. And then the A value you actually just have to solve, although technically it was the y-intercept minus k. Right? I would recommend that you grab a point off the graph to solve for that A parameter, though. It's always a little bit easier. Okay, that's 7.2. Definitely a fair amount of calculator work involved there. Make sure you chip away at the homework. Use your calculators. They are a massively useful tool, and they can often verify the work that we do algebraically.